Hello. So, welcome to the final lecture in the series of geometry in the Sulba Sutra and also in the general discussions on Sulba Sutra that you are having. There are two other videos that I recorded before this lecture. So, those who are interested in a detailed history of the Sulba Sutra and other such related topics may find them in the first two lectures. So, the outline of this lecture is going to be roughly a very short introduction on Sul Sutra because I had already discussed it in the earlier lectures. Then we are going to discuss the topic of geometrical construction of the sum of areas of squares and an elegant proof of the Pythagoras theorem through the same concept. Then the geometrical construction of the difference of the areas of square and the construction of a rhombus on a given area. And then we are going to conclude this lecture and also the geometrical constructions in Sulba Sutra series. So, a very brief introduction about the Sulba Sutra. So, the Sulba Sutra are Indian texts that are roughly dated around 800 BC. They are sort of appended to the Vedic Samhitas, the Vedic texts, and are part of the Kalp Sutra literature that deal with the conduct of Vedic rituals or yagya. So they deal with the construction of these Vedic fire altars or the Vedic yagya Vedis in the earlier part of history. So currently, the Yagyavedis that you may have seen are simple squares inside which Havans and Yagya are conducted. But in that era, it was very elaborate, and the procedure of conducting the Yagya has been very elaborately mentioned in Vedic texts like Shatpat Brahmana, etc. So, to construct those Yagyavedis, we had to use uh, elaborate geometrical methods that were outlined in the Sulba Sutra. So, just for example, like this is one of those Vedis which is in the shape of a tortoise. So, to construct this, as you can see, you need some sort of advanced geometrical tools to be able to correctly measure these dimensions, and then because the dimensions have been elaborately mentioned in the text like Shatpat Brahman and the Rig Veda itself. So to make those dimensions possible in the physical plane, you have to develop a high level of mathematical and geometrical dexterity, which the Sulba Sutra very rightly did so. There are some Sulba Sutras that are known to us. The most famous of them is the Baudhayana Sulba Sutra, and then there are the Sulba Sutra Katyayan and by Upstam. This is one of those Yagyavedis that was constructed and earlier found in excavations in a region of, if I'm not wrong, in Uttarakhand, the Garhwal region. So how do you combine the areas of squares? So basically, if you have two squares, let us say a square of area A and a square of area B, you have to construct a square of area A plus B. Now the problem is that you can do it now very easily because you have calculators. You can take the square root of the areas to get the side lengths, then add them up, square them up, and then duly construct a square. But in that era, you obviously didn't have calculators, and this is a very tedious process. So do you have a simple geometrical method in which you don't need to calculate anything, but just by using elementary geometry can you do it with the help of constructions? So in this method you don't calculate anything, you just use simple geometry to accomplish the task. So this is how the procedure has been mentioned in the Sulba Sutra, in the Bodhan Sulba Sutra. It says that to combine different squares, mark the rectangular portion of the larger square with the side of the smaller one, and the diagonal of this rectangle is the side of the sum of the two squares. So what does this mean? So what it means is that, let us say you have a square ABCD of a given area A, and then you have a square IHGC of a given area B. So you have to construct a square which is the sum of areas of these two squares. So what do you do is that you take this side length IH, you take a, let's say, a rope or something. You put one end of the rope here, the other end of the rope here, and then after that you place it here. So you mark off the exact length as IH here as AF or DE. So take a rope, put one end here, the other end here. Then after holding those two ends, you place them here and also here, so that now you have this AFDE, such that this AF is equal to IH, DE is also equal to IH, GC, all of them are equal. So AF equal to DE is equal to IH is equal to GC. So this is exactly what was meant by marking of the rectangular portion of the larger square with the side of the smaller one. So we marked this edge of the larger square with the side of the smaller one. After you have done this, you join these 2 points to get FE. Now you have a rectangle AFDE. What the sutra says is that the diagonal of this rectangle is the side of the sum of the two squares. So now this rectangle that you have got, the diagonal of this rectangle, that is AE, that will be the side of the square whose area is the sum of these two squares. So AE is the side length. Now you can construct a square taking the side length as AE. So this rectangle AKHE or AEHK is the square. The area of AKEH will be equal to the sum of areas of ABCD and IHGC. So this is what the procedure is told in the Sulba Sutra. Now, how do we prove this, that this proposition is correct? It is a very simple geometrical exercise. So we have already, constructed the square here and marked off the relevant edges and the relevant sides. So this is just a simple, construction that we have done. There's nothing fancy in it, right? So now, after you have completed the construction, what you see is that the area of ABCD, which is this square, plus the area of IHGC. This is what you have to calculate, right? ABCD plus IHGC. This is equal to the area of ADE, this triangle, plus AFE, this triangle, plus IJE plus HEG, or also as ADE plus AFE plus EGH plus EJH plus this square, that is IBFJ. This is exactly what I had written here, right? So once this is known, now what you can see is that, notice that ADE and KIH are similar triangles. Why? Because both of them are right angled. This DE length is equal to IH because that is how we had constructed it. That IH equal to AF equal to D. So DE and IH are same, and also KH and AE are same because this is a square. So these two rectangles, that is these two triangles ADE and KIH are similar, and hence both of these areas will be same. So ADE, you can replace area of ADE with area of KIH. In a similar way, the area of AFE, just write it as it is. EHG also write it as it is. And EHG, which is this E, H, and G, this will be similar to ABK. Again, similarly, because this is equal to this. You can see it very easily, because this is equal to AF equal to IH, and FB is the remaining side. So JH. So FB equal to AB minus AF, and this equal to IH plus IJ, that is equivalent to FB. So these two are exactly same, right? So this is same as this. Uh, yes, so this is same as this or this, and what else? This is a square, so AK is equal to EH. So again, this triangle EHG and ABK are similar rectangles, so this area will also be equal to the area of this. So replace this area EHG by the area of ABK, and again keep FBIJ same. Now note that KIH plus AFE, that is KIH plus wait, KIH plus this KIH plus ABK, right? KIH plus ABK plus AFE plus EJH plus FBIJ, right? This is what we have written: KIH plus AFE, that is this plus ABK this plus EJH this plus FBIJ. This is equal to the area of AKHE, right? So we had started from area of ABCD plus IHGC is equal to the area of AEHK. So we are done. It is the area of this square plus the area of this square is equal to the area of this square, right? So it's very easy to construct the sum of areas of two squares. Just take this side, mark it off here, join it this, and take the diagonal of this rectangle AFED, and this diagonal will be equal to the side length of the square that you want to construct. You don't need any calculators or any other, algebraic calculation to do it. Now, you can also notice that if this square is equal to the sum of the areas of this and this squares, it somehow relates to the Pythagoras theorem also, because the Pythagoras theorem, says the similar statement. Somehow, because the it says that a square plus b square equal to c square. So, like, right, so if you have three squares, let's say, with side lengths a, b, and c, so basically what it is saying is that the area of the square with the side a plus the area of square with the side b is equal to the area of square with the side c. So, both of these are parallel. You have to see the parallel between summing up the area of square and the Pythagoras theorem. So what idea that comes to the mind is that somehow we can you prove the Pythagoras theorem with whatever we have done right now. So how do we do it? It is not very difficult to do it. Why? Because you know what you are seeing here in this triangle, right? Note that this square is the sum of the square. This is equal to the sum of areas of these squares. A, B, C, D, and IHGC. See this triangle ADE. Note that AD is the side length of this square, right? So the area of this square is AD square. And DE, as we had already constructed, IH is equal to DE. So this is the side length of this square. So DE square is the area of this square, right? So AD square plus DE square is equal to the sum of areas of this square and this square. And we had already proved here that the sum of areas of A, B, C, D, and IHGC is equal to the area of this square. And the area of this square is equal to AE square. So we have just basically proved that AD square plus DE square is equal to AE square, which is the Pythagoras theorem in this right angle triangle. AD square plus DE square is equal to AE square. And because these two areas can be anything, any arbitrary squares, hence this is a general proof for the Pythagoras theorem. In any case, it is valid, right? And because the Pythagoras theorem was found in the Baudhayana Sulba Sutra, one can also infer that because this method and the Pythagoras theorem both are present in the same sutra, hence it is highly possible that the people who wrote the Sulba Sutra around 2800 years from now did not only know the theorem but also knew this elegant proof, because they have mentioned this same method to do it. So if they knew how to derive this method and they knew the Pythagoras theorem, they had a proof in front of them. So one can say that the creators of the Baudhayana Sulba Sutra did not only discover the Pythagoras theorem but proved it also in a certain way. Now, obviously, analogous to if you want to sum the area of squares, you would also want to create the difference of areas of two squares, right? So if you have a square, let us say BCD, and you have a square PQDE, you would want to construct a square that is the whose area is the difference of these two squares. So you have to construct a square whose area is equal to area of ABCD minus PQDE. How do you do it? So the consultation that has been given is that you know you have to construct a square which is the area of the whose area is the difference of these two, right? So what it says is that uh, if you construct a square here on this GD, it will be the area of the difference of these two squares, right? But then what is this that we are trying to say? How do we do it? It's very simple to do. Take a rope. Now it is very easy. Just join these so that this is completed. Now what you do is you take a rope, right? This is very clear what you are trying to do. So rope, or in the modern sense, obviously you have a compass, right? So take a compass and create this arc. So point place one end of the compass here, the other end of the compass here, and then rotate the compass. So what you are doing is the same side, that is BC or AD, you are turning it around like this. So this is how you are turning it like this. And then so that when it cuts here, this GE is equal to AD or BC, right? So we just took it from here and then we marked it off here, right? And what a compass does is when you move it, it keeps the length same. So this length FE that was taken from here, or BC that was taken from here, this is exactly the same as GE. So GE is equal to AD or BC. Now in this right angle triangle that will be constructed, right? So just take it from here, mark it here. This will be some right angle triangle that you will be left constructed, right? So take this compass, mark it off here. This is equal to this is equal to this, or AD is equal to GE, and then in this right angle triangle, this is equal to x, or the base is equal to the side length of this square. Now note that in this triangle, by the Pythagoras theorem, it is very easy to see that GE square minus DE square, and GE is equal to AD. So this is the same as saying that GE square or AD square minus x square is equal to GD square. So what do you see? That a square that will be made on this length GD will have the area of the difference of, so AD square is the area of ABCD and x square is the area of PQD. So this square that is built on the side GD will be equal to the area difference of the areas of ABCD and PQD. So this is how you construct a square which has the area as the difference of the areas of two squares. Again, just what you have to do is, once again from the starting, you take the bigger square, place the smaller square inside it, take a compass or a rope, mark off, place one end here, the other end here, cut it off here, mark it here, construct GED. So this length which will be left with GD will be equal to the side of the square that you have to construct. It's very simple procedure. You don't need to take any square roots or do any calculations if you know this method. Now, after these two somewhat involved geometrical calculations, we move on to very simple idea, that is the construction of a rhombus of a given area. So this is given in the Appendages Sulba Sutras. It says very simply that to construct a rhombus of a given area, the only thing that you have to do is you draw a rectangle of twice the area, and we are finished with that. Nothing much has to be done after that, right? So construct a rectangle or a square of double the area, join the midpoints, and you are done. Why? Again, it's very simple to see. If you join these, then it is very simple. Then it is very easy to see that this triangle is equal to the area of this triangle is equal to the area of this triangle. So all that a rhombus does is take half the areas. So it takes one triangle from here, one triangle from here, one triangle from here, and one triangle from here, and each of these triangles is similar to this triangle. So all this line is doing is dividing this rectangle into half. So we are essentially taking half the areas of these four rectangles. So the rhombus that is built on taking the midpoints of the edges is simply uh, dividing the area of the rectangle into half. So this is what Upsum says, very easy geometrical observation to make to construct a rhombus of a given area. Right, so these are three concepts of geometry that we have discussed that were found in the Upstam Sul Sutra and the Baudhayana Sul Sutra. Similar versions are also found in Katyan Sul Sutra, if you notice. So, what I would like to conclude after this lecture and the preceding two lectures is that India had very extensive and elaborate knowledge of geometry as well as algebra, because they were calculating square roots, at least till the fifth decimal place. The square root of 2 had been calculated. So you can see the first video in the channel for that. So because they knew so many details, that is how to calculate a square root to the fifth decimal place, how they knew the statement of Pythagoras theorem. They most likely knew the proof of the Pythagoras theorem. They knew elaborate geometrical construction, that is the construction of sums of square, differences of square, rhombus, isosceles triangle, and a lot of them. So the ideas of algebra and geometry in India, at least 3,000 years before the Common Era, in the Vedic age, were extremely well known. There was extensive research in these areas, in the area of geometry and mathematics, that was going on in that area, driven solely by the urge to create precise geometrical shapes for conducting ritual sacrifices. So what we need to see is that how the ideas of religion and the ideas of rituals are so closely connected with the need to create elaborate mathematical and geometrical tools, to create perfect architecture. In a similar way, the ideas of temples is so elaborately linked with the idea of society and economy. So these are not two different spheres. What we have been, misled to being misled to believing that the ideas of the religion, the sphere of religion, and the ideas of the sphere of science, or the area or of architecture of any modern discipline, are two different areas. It is not exactly so. The need to fulfill the wishes of the first obviously will lead, at least it led in India, to the ideas, to the flourishing of ideas in arts, craft, geometry, and mathematics. So the secular and the religion sphere in India are not that different. And obviously in the Vedic age we had extremely well led developments. So this is the idea of Vedic mathematics, in very brief, what Vedic mathematics encompasses. And in another lecture series that I would like to create next, we will move from the Vedic era into the medieval and ancient era, and then we'll discuss about the discoveries and the ideas of various mathematicians like Aryabhatta, Bhaskaracharya, and especially Leelavati of Bhaskaracharya, which is a wonderful book, wonderful treatise on geometry and algebra. Thank you for your patience.